Now I want to understand what sigma star does when sigma is a transposition. So now we want to understand when sigma is a permutation, is a transposition. So let me remind you, our goal in this video was to prove the theorem that I stated some time back. So maybe it's a good time to recall the theorem. The goal of the video is to prove this theorem. If you have a permutation rho and you have two different representations as a product of transpositions, they're both sigma is are 2 cycles, tau is are 2 cycles, then k and t are both even or odd. And in order to do this, let me recap what we have done so far. We have defined a polynomial and we have defined what is the modification of that polynomial via an element of the symmetric group, sigma star f, and I looked at various examples to explain what is sigma star f, and then I commented that when I take the product of two permutations and apply star, it is same as first applying the first one and to apply the second one to the resulting polynomial, sigma star then apply to tau star f. Okay, and I proved that, and hopefully it is clear to you as we have seen in several examples. Now I want to understand what is tau sigma star f when sigma is a permutation. Again we have seen this in our examples. We got sigma star f was minus f. If you recall, sigma star f was minus f whenever we, in our example, sigma was a 2 cycle. For example, in this example, when sigma is 1 3, sigma tau star f is minus f. Okay, so is this always true that if you have a transposition, then it is star is minus f? Yes, this is always true. Okay, so I am going to prove this, but let me first an easy case of this first, and hopefully that you will be convinced, and then I will give you a more general proof. So first of all, take a special case. As a special case, consider sigma is 1 2 and n is general here. So, and what is sigma of f? Sigma star of f. Sigma star of f, remember what it does. So f, remember, first of all recall what is f in general. Now x is x1 minus x2, f is x1 minus x2, x1 minus x3, x1 minus xn, then you have x2 minus x3, x2 minus xn, and then you have other terms. I am only interested in terms which involve x1, other terms. Right, is this clear? We have x1 minus x2, x1 minus x3, x1 minus xn, then x2 minus x3, x2 minus xn, then x3 minus x4, x3 minus x5, and so on. But remaining terms don't involve 1 and 2, right? So I don't care about that. So now what is sigma star f? Sigma is 1 2. I am only interested in 1 2. Sigma star of 1 2 f will be all these first few terms will change now. So it will be x2 minus x1, right? Then x2 minus x3 up to x2 minus x1, xn. Because the first term 1 and 2 are interchanged, so it becomes x2 minus x1. Second term 1 becomes 2, so x1 becomes x2, and x3 is fixed, so x2 minus x3, x2 minus x4, and then x1 minus xn, so that's x2 minus xn. What happens to the terms involving x2? x2 becomes x1, right? So it's x1 minus x3, x1 minus x4, all the way up to x1 minus xn, and other terms. Other terms are fixed because other terms are terms whose subscripts are different from 1 and 2, and sigma does not change them, so they remain the same, right? Other terms remain the same. So now what is the change now? x1 minus x2 became x2 minus x1, so there is one minus sign, right? One interchange of the variable order, so x1 minus x2 became x2 minus x1. But if you now look at this, no other interchanges have happened. We have just reordered them. x1 minus x3 comes here, x1 minus x4 comes here, x1 minus xn comes here, x2 minus x3 comes here, x2 minus x4, x2 minus xn. So all other terms, so there is only one change of sign. Right, so this is minus f. So remember, I am claiming that if sigma is a transposition, sigma star f is minus f, and I have proved it at least in the special case that you have 1, 2. Okay, so sigma star f is minus f. Okay, now I am going to spend next 5 minutes proving this in general, and you can hopefully you have understood what happened in our examples and in this special case. In this general thing is important to prove, but if you are not, it's more important that you are convinced that it is true based on these examples. Okay, so let me now prove in more general cases. In general, we have sigma star f equals minus f if sigma is a transposition. Okay, so this is what I want to show. Sigma star f is minus f. So I'm going to assume let sigma, it's a transposition, right? So in other words, it's a 2 cycle. So let us say sigma is ij with I less than j. I can always assume that because remember ij is same as ji. So I and j are different obviously. So I can put the smaller one first and the bigger one in the second position. It's a cycle. So ij is same as ji. So I can always arrange them so that the first one is the smaller one. And now let us investigate what is sigma star f. Okay, so let us investigate what is sigma star f. This involves us, this requires us to investigate what is sigma star of a particular term in f. Okay, so consider a term of the form xu minus xv, right, where u is less than v. Remember, these are, because I have used I and j to denote sigma, I have now used u and v to denote a term. This is a typical term right. F, remember, consists of products xu minus xv, where the first index is strictly smaller than the second index. In order to determine what is sigma star f, I need to see what it does to a term like this. Really what we need to do is, we have to figure out, to find what is sigma star f, we have to determine how many terms of the form change sign, right, under sigma, right? Because if you know how many forms change how many terms change the sign, then we know what happens to f. If the number of changes is even, you have sigma star f will be f. If the number of changes is odd, sigma star f will be minus f. So when does, the question is, so the question we want to address is, the question is, when does this change sign? So when does xu minus xv under change, always under sigma, to xa minus xb with b strictly less than a, right? When does this change sign? When you have a bigger thing minus a smaller thing. You start with a smaller thing minus bigger thing. So here of course u is less than v. You only start with such a term, u less than v, and see when it changes to b less than a. The second term less than the first term. So in order to address this, let us consider various cases. If u and v do not belong to the set ij, right? If u is different from I and j and v is different from I and j, xu minus xv does not change. That is clear enough, right? Because if sigma, what does, so remember sigma star of xu minus xv is x sigma u minus x sigma v. So we are now focused on when is sigma u, for what sigma u is strictly bigger than sigma v. So we are interested in for which sigma u becomes strictly more than sigma v, right? The first index is strictly bigger than second index. The trivial case would be if u and v are different from I and j, then sigma u is u, sigma v is v, right? Because if and sigma is ij, if u and v are both different from I and j, sigma of u is u, sigma of v is v, so this does not happen. Now let's consider the other cases. So we have remaining cases are the following. Case 1. So we can have u equals I and v equal to j. So remember, u is strictly less than v and I is strictly less than v. So you can have u equal to I, v equal to j. Then what is sigma star of xu minus xv? This is x sigma u minus x sigma v, but u is I, so this is x v minus xu. So this is one case where sigma u is of course bigger than sigma v. So in this case the sign changes. So this is one situation where sign changes. Let's take case 2. Let's take u to be I and j is something else. Okay, so v is something else. So if you take u to be I, so then what we have is, let's see, in this case, see, remember I have already dealt with the case that u is different from I and j, v is different from I and j. So one of them must be u, one of them must be j. If one of them is I, the other is j, both happen, then that's case 1. Other cases u equals I and v is not equal to j, let's say. Okay, in this case what do we have? We have u equals I, which is less than, we have two cases. So let us suppose that, let's compare v and j. So if v is less than j, So you have u equals I, right? So this is a sub case of case 2. In this case, what happens to xu minus xv under sigma star of xu minus xv? This becomes this is x of sigma u minus x of sigma v, but u is I, so this is x of sigma I, which is j, and sigma v, remember v is different from I and j, so this is just xv, right? In this case, a change of sign happens because I am assuming v is strictly less than j, so sign change occurs, right? On the other hand, I am still assuming u is equal to I, but let's say j is strictly less than v. V is different from j, so j is either strictly more than v or j is less than v. In this case, what happens? So sigma star of xu minus xv is xj, xu will go to x of sigma u, which is j, and v is fixed, v is different from j, so this is xj minus xv. But in this case, you have j strictly less than v, so here there is no sign change. Right, because you have smaller minus bigger, so there is no sign change. Sign change only happens when you have bigger minus smaller. Here j is strictly more than v, but you have xj minus xv. What about case 3? U is different from I and v is j, right? In this case, remember u is strictly less than v always. So in this case, we have again two possibilities. Either u is less than I and I is less than j, which is equal to v. In this case, what happens to sigma star of xu minus xv? Xu, u is different from I and certainly it is different from j, so this is xu, and v is j, so this is xi, right? Sigma of v is I, and I am assuming u is less than I, so there is no sign change. Right? Now let's consider the last sub case of case 3. I is less than u and j is equal to v, in which case sigma star xu minus xv is xu, again u is different from I and j, so that is xu, and v goes to I, v is j, so v goes to j under sigma, and here u is strictly more than j, so there is a sign change. Sign change occurs. Okay, so let's now see how many times, let's count how many times sign change happened. Let's count how many times sign changed. Sign changed, remember, in case 1, that's one case, u equal to I, v equal to j, so that's one case. This is corresponding to, okay, so let's once for u equal to I and v equal to j. Okay, now when else it happened? In case 2 it happened whenever, remember I and j are fixed, we are counting how many times u v have the property that sigma u is strictly more than sigma v. So it happens when u is I and v is j, right? So v is strictly between, when u is I and v is strictly between I and j. How many numbers are strictly between I and j? So if you list all the numbers 1, 2, I, then you have I plus 1, I plus 2, j minus 1 and j. So it has to be strictly between. So what is the possible range for this is U, and J has to be among these. V has to be one of these, right? How many numbers are there? So V has, for U equal to I, V has J minus 1 minus 1 I choices, right? You take first J minus 1 numbers and remove the I that V cannot be. So there are these many choices. Now on the other hand, when V is J, also we have sign changes. When V is J, the sign change is when U is between I and J. U is strictly between I and J. Okay, so again the same concept. So you have 1, 2 up to I plus 1, and J minus 1 and J equals V. So U is among this. Okay, so there are for V equal to J, there are again J minus 1 minus I choices for U. So now the sign changes. So finally the sign changes once when U is I, V is J, J minus I minus 1 when U is I, and J minus I minus 1 when V is J, and this is 1 plus 2 times J minus I minus 1. So this many times the sign changes. So now we are able to finally say what is sigma star F. Okay, so it is, and this remember is an odd number. No matter what I and J are, twice this number is even. So 1 plus that is an odd number. So you have odd number of sign changes. So this is sigma star. We can conclude this. Right? Sigma star F is minus F. So this is what I have said some time ago. I claimed that sigma star F, after doing an example, I said in general sigma star F is minus F. Okay, so in the last 10 minutes or so when I proved this, it is possibly confusing to you, but this is the complete proof. Please, if you need, please go over the video again, and hopefully it is clear to you that for any transposition we have sigma star equals minus F. So now we have proved two things. Let us recall. We have proved two facts. One was sigma tau star F is sigma star of tau star F. Here sigma and tau are arbitrary permutations of Sn. The second is sigma star F is minus F if sigma is a transposition. Right? We have proved these two facts. Sigma star F is always minus F if sigma is a transposition. So now even if the previous 10 minutes that we took to prove 2, if it's not completely clear, please start focusing again. You can go back and hear that proof again later if it's not clear to you. But it's now easy to conclude the theorem. So now we get back to the proof of the theorem. Remember, in the proof we have two possible representations of rho as a product of transpositions. We wrote this as sigma 1 through sigma k product, also as tau 1, tau 2, tau t. So we are trying to show that we want to show k and tau have same parity, which is to say that they are both even or both odd. One is even means the other must be even. One is odd means the other must be odd. So let's now, to prove this, let us look at, so the proof is almost done, okay. So proof will be now pleasant, having proved the two results. Let us look at tau rho star f. Because rho has two representations, we can compute rho star f in two ways. Okay, rho star f using the first representation is sigma 1, sigma 2, sigma k star f. Okay, that is because rho is that, sigma 1 to sigma k. Now using the first fact that we have proved, sigma tau star f is sigma star of tau star f. See, we have proved it for two permutations. Obviously the same carries over for three permutations or four permutations. We have to iteratively apply the same principle. So this is sigma 1 star of sigma 2 up to sigma k star f. Okay, and then you repeatedly do this, it becomes, and sigma i's are, remember, transpositions. And what does the second property say? Sigma star f is minus f. So actually let me write it like this. This is sigma 1 up to sigma k minus 1 star of sigma k star f, right? So I split off at the last stage. Sigma 1 through sigma k minus 1 I apply and then sigma k star f. But what is sigma k star f? Because sigma k is a transposition, this is minus f. Then you apply sigma k minus 1 of this. So you repeatedly apply this. We get what? For each application of sigma I, we introduce a new negative sign. So this is minus 1 power k f, right? If it was k was 1, you get minus 1. If k is 2, you get, so I'll just do this once here so that it becomes clear. So sigma 1, sigma 2 are transpositions. Sigma 1, sigma 2 star f will be sigma 1 star of sigma 2 star f. But sigma 2 star f is minus f. So this will be sigma 1 star of minus f, but that is same as minus of minus f, because sigma 1 star is changes the sign. So this is f. So now if you have a sigma 3, so f is, so this is minus 1 whole squared f, because there are two terms. If you apply it once more, it will be minus 1 power 3, because it will be minus and so on. So it is minus 1 power k f. On the other hand, we also have rho star f is tau 1 up to tau t star f. But this again repeatedly applying tau 1 by 1, this gives tau minus 1 power t f. But now rho star f is what it is. Rho star f is either minus 1 f, minus f, or f. Right? Rho is a fixed permutation. So rho star f is either f or minus f. So we have minus 1 power k f is equal to minus 1 power t f, right? Because both are equal to this. This is equal to rho star f. This is also equal to rho star f. So minus 1 power k f is equal to minus 1 power t f. This means minus 1 power k is minus 1 power t, right? Because if they are both f, then minus 1 power k is 1, minus 1 power t is 1. If they are both minus f, minus 1 power k is minus 1, minus 1 power t is minus 1. We don't care what it is, but they are both equal. This implies k and t are both even. See, minus 1 power k is 1 exactly when if and only if k is even. So if k is even, minus 1 power k is 1. So minus 1 power t must also be 1. So t is even. Or if k is odd, minus 1 power k is minus 1. So minus 1 power t must be also minus 1. So k and t are both odd. So this completes the proof of the theorem. Which is exactly what I wanted to prove. So the theorem says that if you have possibly different representations of the same permutation, the number of times you have transpositions there may not be same, but whether they are even or odd is the same. So now using this, we have a very important definition. Let sigma be a permutation in Sn. Sigma is said to be even. Okay, so this is what we want to define. So sigma is said to be even sigma is an even permutation if the number of transpositions required to express sigma as a product is even. Okay, this is perhaps, it's unnecessarily long sentence, but what I am saying is that write sigma as some sigma 1, sigma 2, sigma k, where sigma I are 2 cycles or transpositions. Okay, sigma is even if k is even. So after you write sigma as a product of transpositions, we can determine if sigma is even if k is even, sigma is odd if k is odd. Now you might ask, because the representation is not unique, why is this definition well defined? Because sometimes you might require 3, sometimes you require 5, but the theorem now comes in. What is the theorem that we prove? Say, even though the number of transpositions required might be different, in each representation we will have the same odd number or even number. So in one representation if it's even, then in all other representations it's even. So it's a well defined notion. So this notion well defined because of our theorem. See, the notion will not be well defined if some product representation has 3 transpositions, another product has 6 transpositions. Then would you define it as odd or even? One requires 3, the other requires 6. But the point is that doesn't happen. If one representation requires 3, then any other representation will require odd number. It may not be 3, but it will be odd. So we are guaranteed that they are all odd. So we can define it to be odd. Otherwise we are guaranteed that they are all even. So it will be even representation. So okay, so let me stop the video now. So this theorem is very important. It is an important theorem because it is required in order to determine whether we can systematically correctly define an even and odd permutation. So this notion of even and odd permutations is very important in symmetric groups. Thank you.